Okay, hello everybody, welcome to this webinar about the software function AFC, Adaptive Feed Control. My name is Michael Wiendl, I'm trainer for NC programming at the training department at Heidenhain, and I want to show you in this webinar the function AFC. If you have questions, do not hesitate to ask. You can use after this webinar the question window to ask questions if there are any questions there. Okay, function AFC, Adaptive Feed Control. It's a software option and it's available on both Heidenhain high-end controls, the ITNC 530 and the TNC 640. Also, the AFC function is part of the campaign Dynamic Efficiency. When you visit a Heidenhain booth on any show over the world, you will learn about this Dynamic Efficiency function. These are different software options to become better during a heavy machining roughing process. So, starting with the application of AFC. So, what can we do with AFC? The first is that we can bring the tool to a longer life, because with AFC we can detect that the tool will get a bad cutting situation, and so we can reduce the feed rate not to get too much pressure on the tool, and so we can just protect the tool break or the too much pressure to the tool. We can also optimize the machining time, because we can detect when the tool is not in machining process, and during this time we can just make the feed rate higher, and so we get a better machining time. Also, we can avoid the tool breakage because of reducing the feed rate to reduce the pressure, and also we can protect the machine kinematics. If the tool gets worse and worse, it's more and more pressure to the machine, and if the machine construction is not so heavy, we can also destroy machine parts. When we don't use AFC and the tool will get in a bad cutting situation. So, for this, it's important we work with the spindle load, and for this we need to know the normal spindle reference load that we learn during the first cuts when we use AFC. And when we know the spindle reference load, we always try to come to the learned spindle reference load, and we can and to reach the learned spindle reference load, we can go up and down with the feed rate just to reach the learned reference load. So, what happens when we go through a material? So you see here we have a workpiece, and we want to go through with the cutter in the X plus axis here, for example. And in the diagram you see here the behavior of the feed rate. So at first, when we reach the material, we have an air cut, then we go into the material, then we speed up, then we are doing the feed, the machining process, so the feed rate is high. Then you see we have here more material, so the feed rate goes down. The green line is here the programmed feed rate. So you see we are most of the time over the programmed feed rate, and when there is more material we are under the feed rate. This is an interesting point. For example, when we do not reduce the feed rate, it could happen that the tool will break after some while when there is too much material on the tool. So AFC is working with a table, the AFC.tab. And inside of the AFC.tab you just set different options for AFC. So you can, every line in this AFC table is an own strategy. So normally we are doing for every tool an own line in the AFC table. So you see here the different lines. So every line is a different strategy. Then we make a name for the strategy. This name we will see later also in the tool table when we combine the strategy with the tool in the tool table. Then we define two feed rates, the feed rate minimum and the feed rate maximum. This is always the feed rate in percent of the programmed feed rate. So, and between this Fmin and Fmax values, the control is allowed to move the feed rate to reach the learn spindle reference load. When the control detects an exit of the material, then we can switch to feed rate in the air, FIDL. That's feed rate in the air. So when there is no the control did not detect any material, so no spindle load, then we can switch to the feed rate in the air. So again, a higher feed rate. Always percent of program feed rate. The next step, the feed rate when we entry or exit the material. So when we detect an entry or exit from the material, we just reduce the feed rate to, for example, 90% of the program feed rate. The column overload, OVLD, here we can define what the control should do when she needs to go with the feed rate under the F minimum. So you see feed rate in percent as of which there is an overload reaction. So when we need to go under the F min defined feed rate, then the control will make the overload reaction what we define here. So M is a special AFC macro, F is an NC stop, S is an immediately perform NC stop, and E is only an error message on the screen. So there you can define what the control should do when it is not possible to go with the feed rate lower to reach the learn spindle speed, as we define in the F minimum column. Then the P out. This is when the control should detect an entry or exit out of the program. So spindle performance in percent of the reference load as of which the tool exit is output. So when we just detect input, exit, or entry in the material. And the sensibility, there we always start at first with 100%. You can make it over 100%, then it's more aggressive. You can make it under 100%, then it's more relaxed, the sensitivity of feed control. So it's just there's with more experience with AFC, you can work more with this sensitivity. Normally we start always with 100%, and then we go on with the next, and then we try our machining processes. Okay, so our example again, and what the control will do. So you see we have here our spindle display. So the spindle has at the moment no load, and the red line should be the normal spindle load, so the learned spindle load. So you see we detect an entry into the material. So the first step, we reduce the feed rate to the value of Fn, so 90% of the program feed rate. Okay? So, and now this line is the sensitivity. So when we make it more relaxed, then this line is longer. When we make it aggressive, then this line is shorter. So, and now the control tries to work with the Fmin and Fmax to reach the S nominal. So you see here we have not so much material, so we are under the S nominal, so the control will go to the Fmax to reach the S nominal again. On this step now the material goes higher, so what happens? The spindle speed or the spindle load goes over the S nominal. So what happens? The control will reduce the feed rate, and what happens now? The spindle load goes up and up. So what happens? Perhaps the tool gets worse, so the cutting situation becomes worse, and so we need to reduce more feed rate to prevent the tool breakage, for example. And this is automatically done by AFC. So AFC is just working with the feed rate and always wants to come back to the load spindle, to the learn spindle load from the beginning. So how can we program it? So we have here that at first we need the AFC table. So in the TNC partition or in the TNC table partition on the 640, we need the table AFC.tab, T-A-B. And there we can define our strategy. The next step is then we need to combine our strategy with a tool. So this we can do in the tool T. So in the tool T we have the column AFC, and there we can just tell the control which strategy she should use for this tool. Then we start at first when we have a new program and there was no AFC done before, then we need at first start learning. So during the learning process the control just recognize the highest spindle load what we get. So because of this it's also necessary that you have good spindle load. For example, if you are doing finishing, there you do not get a spindle load. Or also when you're doing, when you have a small miller, for example, normally with an HSK spindle 63, for example, and you have a 6mm diameter cutter, then that's there is no spindle load. So we need spindle load. So more than 6% spindle load we need to that we can work with AFC. When we finish the learning process, then we go to controlling. And during the controlling process, the AFC varies the feed rate between the Fmin and Fmax just to reach again the learned spindle load from the beginning of the AFC process. So the NC program is looking like this. At first we make a tool change, then important to switch on the spindle before we switch on AFC. So the spindle should run before we activate AFC. Then we can activate AFC. This could be done by an Heidenhain function. We talk about this later. It could be done by an M function of the OEM, by a cycle from the OEM. Then we make our machining process, and then the next step is also important. We need to switch off AFC. Also Heidenhain function, M function, or a cycle. Because when we switch off, we can make a new learning process for a new strategy. For example, when you are doing with an end mill, with a diameter 16 end mill, you want to do an outside milling, full cut, and a trochoidal milling. These are three different machining operations with three different learning spindle load. So, and because of this, you need to also learn 3 times. And this you can do when you switch AFC after the machining also off. So Heidenhain offers also AFC function for the NC program. It's available, you see it here, since software 04 from the iTNC and also software 04 from the TNC 640. Before, we always need an M function or a cycle from the OEM, otherwise AFC could not be programmed. So we find this function in the special function key, program functions, and then the AFC function. And there we have 3 soft keys. Function AFC cut begin. There we can say, okay, from this time AFC should learn, or if it already had learned, then AFC should start automatically with controlling. Or we can also say we want to learn 10 seconds. So after 10 seconds the control switch to controlling. Also possible, we can define a distance. So distance 100 millimeter. After 100 millimeter the control will automatically switch from learning to controlling. And we can also define a spindle load. When we have more experience with AFC, then we can define, or then we know, okay, we have a face miller diameter 60, and we want to make face milling from steel, and I know for this tool, with this material, with this machining process, I have a spindle load from 60%. And then I can say, okay, function AFC cut begin load 60%, and then the control automatically use this 60% as learn spindle load and starts directly with controlling. So that's a possibility when we have more experience with AFC, that we can define a direct spindle load for the machining process. And then AFC cut control. This is just, you can also say I only want to program function AFC cut begin, and after the first 3 set steps from a CAM program I want to change automatically to controlling. And for this we can use the function AFC cut control. And function AFC cut end is end of the cut, so the line in the AFC tab would be in the dependent file would closed with this sentence. Yeah, when we have some or with one tool more machining different machining operations, we can use the structure here. We make a tool call, then M3 spindle on, then we switch on AFC. We make our first machining, we switch off AFC. So in this machining we at first learn, and then we can switch to control. And in the second machining, the same, AFC on, machining 2, so we learn again, and we switch it off with the AFC off function. So this is a possibility when I want to do with one miller, for example, a half cut, trochoidal milling, and a full cut. Then I have 3 different spindle loads for one tool. I can activate I need to activate AFC also by a soft key, AFC on. AFC will be automatically switch off when we change the override for the feed rate more than 10% in minus direction. And also the feed rate potty must be over 50%, otherwise AFC is not working. So the soft key need to be over 50%. The potty needs to be over 50%, otherwise AFC is not working. When we work with AFC, we get different depending files. We get the first file is the program name with .h, .afc, .dep. There is the copy of the active strategy for this program. So we can change the strategy just for this program. And the afc2.dep, there is the result of the AFC process. We will look about this later in the programming station. So here's the result of a screen of the result table of AFC. So the first 2 lines are the tool number and index. the programmed spindle speed, the difference, the learning time, so how much or how long the control learned, the control time, the difference, the maximum spindle load, and the spindle load reference value. So that's the P-ref is the learned spindle load. Then the overload reaction, if there is something defined, and also the block number of cutting starts. So where I programmed the starting of AFC. So some points also for AFC. So we can detect the entry in the material, we can optimize the feed rate for it, we can work against overload for the tool, we can also save the maximum value for the spindle for later process. So when we now know, okay, our P-ref was 53%, then we know, okay, for next machining we can use this also. We can also switch over to higher feed rate in the air. That's important when I have some movements not in the material. And AFC is automatic inactive during Fmax, so maximum feed rate programming. So the machining example is a workpiece like this. There we have a rectangular stud with a 10 degrees angle, and then we have a shoulder milling here, and the next step is a trochoidal milling slot. Program runtime without AFC is 5 minutes 20, with AFC 4 minutes 15, so time saving up to 21%. And this example we want to look later at the machine. We now go to programming station. And in the programming station, I prepared a program AFC. So at first, we need in the control, we need to check if the AFC table is there. So it's already here. If it's not there, then we can just create a table AFC tab. Then you can select the table format. Then we can select here, okay, the AFC tab. And now you see you can also create a new AFC table on the control. The name must be always AFC tab. So that's always the active AFC table. So and here you see I added a new strategy for the end miller diameter 16, the F minimum 80%, F maximum 120%, for feed rate in the air 200%, the F entry 100%, overload, an M function, so a macro, what's defined in the machine parameter, P out and sensitivity like in the standard value above here. So the next step is then in the tool table. I have my mill diameter 16, and here I can go to the end of the line, and here we have the AFC. So, and here we can just with enter we can select which strategy we want to use. So you see here these are the names out of the AFC table with the correct strategy here. Okay. So, end of block, and we switch back to the program, last files, AFC. Okay, so, and here I make my tool call M3, and what I want to do, I always like to show AFC together with the trochoidal slot cycle, 275. So I just define an open slot with a width of 20 millimeters and 20 millimeters deep, 20 millimeters plunging deep, and a side step allowance for side of in feet per revolution, was it, with 0.5 millimeters. So, and this I want to do now with AFC. So I program special functions, program functions, function AFC, and function AFC cut begin. So, and now I can say with a time, with a distance, with a load. I only want to start now learning AFC, and next step is then my machining, and the finishing here I want to do without AFC, so I switch AFC off after the M99 of the cycle with function AFC cut end. So that is the first operation. Then I switch off AFC and I make the finishing again. Then I make a datum shift. I want to do the same slot on a different position, and now I want to use a time for learning. I want to use 20 seconds time. Of course, when we use time, we need to be sure that inside or in this time we will reach the maximum spindle load over this machining process. So the best is always to make a complete learning process over the first workpiece, and then we use this knowledge for the second workpiece. But if we only have one workpiece, we can also use a time, or later here we can also use a distance. So distance, we say 200 millimeters, because we are doing a toroidal milling. And there you need to just to calculate the length of the radius, because we are always doing a circle movement, that we have enough distance for learning there. Okay, so we go to single block AFC. So at first, important that you activate with the view, programs, and status. Okay, and then you go here to the writer AFC. Okay, there we see the everything of the AFC function, and also that the soft key AFC is on. So we start now with our program. Take in the tool M3, function AFC cut begin. You see now teach in is there. So now we are learning, and now we start with our learning process. And during the learning process, I can now say AFC settings and exit learning. Then we stop learning and we go to controlling. So we start now with our spindle ref load of 58% and do the learning process here. Okay, function AFC cut end. The next step is finishing without AFC. You see AFC status is inactive, so without any material in it. Okay, then the second slot, and we already programmed function AFC cut end, so there again will be learning. So you see teach in and reference load of the AFC is active here. Okay. And finishing again. So you can also, if you want to try it, you can also do it on programming station. This is also possible to do it on the programming station here. Now, and the last one, the last slot is now with a distance 200 for learning. Also M99, and again our reference load of the spindle. now controlling and finishing without AFC. Okay, so now we get a result. We can see it on the AFC setting. So and here you see the result. So we have 3 times the tool mill diameter 16. That's why we programmed it function AFC cut begin, machining process, function AFC cut end. We did this 3 times. Because of this we get 3 lines here, so 3 different possibilities for our tool. So here we see the values from the AFC table, the Fmin, Fmax, feed rate in the air, feed rate entry, the overload reaction, and the learned reference load of the spindle. And also we have an evaluation, so the result of the AFC process. So you see here, okay, we have a control time of 1 minute 20, so we saved 1% time for our example here on the programming station. So that is just the result of the AFC. And these values are always stored directly where the program is. So you see here afc.h, and there we have the dependent files for this program here. Okay, so the next step would be the video from the machining process. Start with the video here. So you see the first process here. So you see the first process is face milling without AFC active. So just simple face milling with a face miller. We are using the cycle here and there. You see it's not active. You see it in the motors here in the screen of the control, inactive. So next step, we put in a diameter 60 tool, and with this diameter 60 tool we want to do an outside rectangular stud. And you see now the learning. So the reference, the P-ref, is now the learning situation from the control. So you see mode learning. So we are now making some rounds with this tool and can just learn the maximum speed. So of course with this special covering around of the material, the best would be to make a complete learning process over the workpiece, but here we change now. We go to the table, the AFC table, and soft key and go to exit learning. So you can always stop learning manually by the soft key in the AFC table. So here you see the AFC table, and then you can say stop learning. And now you see the behavior of the machine. When we are outside of the material, the control goes faster. That's the feed rate in the air. And when we are inside of the material, we stop a little bit and then we go on. So now we can save time because of the air cuts of this workpiece here. Faster. And you see also the override and the spindle load in the AFC table here. So next step is then the shoulder milling. Also here, next machining process. So what do we do here? We just learn 3 cuts, and now we are change it with function AFC cut control to the controlling way. So we can also save time and also protect the tool against higher pressure here. Okay, then we change the tool. The next tool is a diameter 12 end miller, and with this tool we want now a trochoidal slot. So the same, also learning again because we have a new machining operation. Okay, and now we stop learning again manually, and now you see what happens. This is a good example because in the trochoidal slot milling you have 180 degrees in the material, 180 degrees outside of the material, and so you can use there this is a very good machining operation for using AFC to get a better cutting time here. In this simple cycle you only need to program the neutral way, the neutral line of the machine, and so you can easily work with trochoidal milling, and especially for deep slots this is a really good cycle for programming. Now you see slot is open, so we can go also faster between the machining processes, and then it's over here. And then the finishing. So finishing you should normally do without AFC, just to get the better cutting conditions. And now there is the result for it, and especially interesting is the machining time. There was a saving up to 21% for this machining time here. Okay, so that's all from my side from AFC. So you can use AFC for optimizing the program, for a better cutting time, to protect the tool, and this is a very good way to handle AFC. So if you're interested in AFC, you can contact Heidenhain or also your OEM. There is the possibility that you can test for free the AFC function up to 90 days. If you just want to see how it is working, then you can contact Heidenhain to get a free license code to test AFC. And if you're interested, you can buy it, and then you can use the AFC function as long as you want. Okay, thank you very much for your attention. If you have any questions, you can contact Heidenhain. The best way is always the email. It's 3103@heidenhain.de. That's the email address from our service department, from the NC service, and there you can find always support from Heidenhain. Yeah, okay. Then thank you very much. Have a nice day and see you next time for next webinar.